Okay, let's begin. We're going to cover a fair amount of stuff today and Friday, and between them, it's the really neat applications of derivatives. We're going to look at graph sketching and how that's done, and keep in mind what we do is graph sketching, not graphing. It's a looser type of it. We're going to look at the important pieces of data, but you don't need to be an artist to do very well in this. Simply a matter of knowing what things look like once you have the numbers that are attached to them. Before we get to it, I'm just going to give you a small exercise to play with. And this is something that I give my, my online calculus course every year. And keep in mind, they get this during the summer semester. So they then have to figure out what all of it means. And it generally takes them about 3-4 days to come up with a solution which is tremendously homogeneous along the entire class. So the idea is that we are going to build a triangular truss with let's call it ABC, with AB horizontal and of length 20 meters. Okay, C is 10 meters above AB. All right, so that's sufficient for it to be a triangle, right? There will be a force of, I don't know, 500 kilonewtons applied at C, and then it's your choice. The easy thing is to have it applied horizontally, but just in order to make things a little bit more exciting, maybe applied at a bit of an angle. So, dealer's pick over here. You can go with horizontally. You can go with 30 degrees below the horizontal, whatever you like. And A is pinned, B is on a roller. Okay, find where we should place C to minimize the largest force in the truss. Not an easy question, but you know everything you need to know about it. You know enough about how trusses work, you know how all of the vectors work, and you know that once you do all of that, you take the derivative and set it equal to 0. Okay, so play with it, see what you can do. If you come up with something, fantastic. If we need to go over this in class, we'll do that, or if you'd rather, we can toss this to the Math Success program, have a seminar on it, whatever people prefer. But I think there's useful stuff over here. So that intersection of the different courses that you take. I've made the claim a number of times. My ideal, my goal, is to someday be able to take the class of first-year engineers, and in December bring them in, put them in a single room for about 8 hours, and give them one question. You solve this question, you get MAT186, MAT188, and Civ 100. You get the credits for all 3 of them, and you get a good grade for all 3 of them, and off you go. And if you don't, then it's some serious T program time that you're going to have to take the next semester. But for me, I think this should be our goal. We should attempt to get to that point where we can ask you just this one question and see just how many courses we can force you to think about at the same time. Right? So, I don't know, add something about write up a proper presentation of this in order to be able to explain to a client your solution. Something like that in order to add a little bit of APS 111 in there. Okay? Good. So, questions on it? We understand the terms as stated? All of that is okay? Good? Fantastic. Okay. Have fun. Enjoy. If you don't want to deal with this until, say, Tuesday at 2 p.m., that's fine too. Okay, you can wait until then. The problem will keep. All right, what we're going to do today is going to begin with the idea of looking at what the derivative means for the function. So we've already seen that when f prime is less than 0, that means that f is decreasing. And I should be more precise, f prime is less than 0 on an interval. Right, at an individual point, we don't necessarily know too much, but on an interval, f is decreasing on that interval. When f prime is greater than 0, then f is increasing. Okay, and we can start playing around with this. So we can look at what happens when we take a second derivative. So if we have f double prime is greater than 0, and when f double prime is less than 0, we can examine those cases and see what happens. Now, if I tell you that the derivative of the function is negative, is the function itself positive or negative? How many think it's positive? How many think it's negative? How many have realized that it's a trick question? Not bad, not bad. Okay. Right? The value of the function itself has no bearing on the derivative, because I can move my function up, I can move it down. That doesn't change whether it's increasing or decreasing. Right? So if I draw something that looks like y is equal to x cubed, roughly, 10x, I don't know, something like this. It doesn't matter if the x-axis is here, or if the x-axis is here, or if the x-axis is here, this thing is increasing throughout. So the value of the function does not matter. So same thing happens over here. When f double prime is greater than 0, my first derivative could be positive, could be negative. Right? And I don't know which one, and I don't care. But it tells me something about it. When f double prime is greater than 0, that means that the first derivative is moving higher. Okay, don't think of it as getting larger, because it isn't necessarily. If it was positive to begin with, it is becoming a larger positive number. But if our function started off decreasing, then that slope is moving up, which means that the function is slowing down on its way to hopefully starting to go up. So we have a term for this, where when this happens, the function looks like this. We could be on the left side of it, where f prime is negative. We could be on the right side of it, where f prime is positive. Right? Both are valid. Similar thing happens over here. Right? That one looks like this. So this is f prime is positive. This is f prime is negative. An excellent idea for exercises is to look at functions and just read off of them what the derivative and second derivative would need to be like. Right? And we're going to do a seminar like that in the Math Success program, most likely next week. Bits of terminology for them. This, back when I was your age, was called convex. But then we decided that, well, this was called convex. This guy over here was called concave. And then we decided that that was too confusing for people. And so in our way of insulting your intelligence, we decided to call these guys convex up, and these guys are convex down. I think that's pretty stupid terminology. If you're going to go for very low-level fundamental terminology, this is a valley, this is a hill, and you can use that terminology around me, and that's perfectly fine. You understand it. That's sufficient. Yeah. Yeah, so you can play around. Sorry, concave upward? Weird. Okay. Concave upward. Oh, sorry, concave. No, you know what? You're right. You're absolutely right. The problem is once you get rid of one of them, who cares which one it is? Right? What you're really looking at is the up and down more than anything else. I like the convex and concave. For one thing, they helped me memorize which one is which. Right? So convex ends with ex, and the function y is equal to e to the x is a convex function. Concave looks like the mouth of a cave. It's stupid, right? Let's see you try to forget it. Okay? It's going to be another 3 decades, and you'll still look at it and you'll go, oh, concave, yeah, it's the one that looks like a cave. It works really well. Those were the ways that I had memorized it, and then one of my students a few years ago came up with something even stupider and even tougher to forget. We like it when things are positive, right? They're significantly easier than when they're negative. So we smile. And when they're negative, we're sad. So we frown. Try to forget that one. Right? A good mnemonic is not necessarily one that is clever. It's one that is easy to remember. These are good mnemonics. So that gives us an idea of how to play around with first derivative and second derivative. When we have these, they allow us to figure out whether a point is a maximum or a minimum. When we have a critical value, we can look at it and we can try to examine the function itself and get a sense of whether the value is a local maximum or a local minimum. Now, many high schools, it seems like a greater and greater percentage of them, teach both the first derivative test and the second derivative test, and then say, use the second derivative test all the frickin' time. Which is horrible, because the second derivative test doesn't always work. And so every now and then, you have to go back to the first derivative test. On top of which, in order to have gotten to the second derivative test, you must have already done all of the groundwork that's required for the first derivative test. So why bother? Why take that second derivative? So even if we take something really simple, let's take y is equal to x cubed minus 12x. What the heck? Plus 2. Okay? If we looked at this one and we wanted to find the critical values, right, the critical points for this function, and then figure out for each of them whether it's a positive or a negative. First, take the derivative. It's a simple enough application that we can just do this with prime notation. We don't need to write down, take derivative both sides, anything like that. Just jump straight into it and set it equal to 0. Pretty straightforward to solve. X squared is equal to 4. X is equal to plus. It's not that I did the arithmetic wrong, it's that I misspelled the number 1. So, the number 2. X is equal to plus or minus 2. Okay? In order to have figured this out, I had to find the derivative. I had to figure out whether the derivative is equal to 0. So I might as well, by this point, do a number line where this is negative 2, this is positive 2. And ideally, if I did this by factoring instead of doing that, so if I had done this as 3 times x plus 2, x minus 2 is equal to 0, makes things really easy. This is going to be positive, this is negative, this is positive. Right? Any complaints about that? Any questions about it? Because once you agree to this, then I'm going to go through the rest of it in like 3 seconds. So are we okay with it? Okay. So positive means that f is what? Incasing, absolutely. Minus means decreasing. Positive means increasing. Is this a maximum or a minimum? Yeah. There is no way in hell that that's going to be a minimum. Right? The function goes up, function comes down. It has walked up the hill, it has tumbled back down again. That must have been the maximum. Over here it started by going low, then it went high. And it doesn't matter what actually physically happens at that point. The first derivative could have been 0, and we could have had a nice horizontal point, right? A point where the tangent is horizontal. Fantastic. Or it could have been what we call a cusp, where the function does this, which we get, for example, if we look at y is equal to negative the square root of absolute x. Right? Square root of x comes in vertically, and so we're going to have vertical in both directions, and we're just flipping it upside down. So the terminology for this is a cusp. We could have something like y is equal to absolute x, which we refer to as a corner. There are quite a few ways in which things can go horribly wrong at these critical points. But the first derivative test tells you, regardless of what has happened, whether it's a maximum or a minimum. If you have something like y is equal to the cube root of x, then y prime is equal to 1 over the cube root of x squared. You set that equal to 0. Obviously, there's no point where it's equal to 0, but there's a point of discontinuity, and you get positive here and positive here. Your function is continuous. It's increasing up to here, and it's increasing after that. Is this point a maximum? Nope. Is it a minimum? Also no. Therefore, it's neither. It's allowed to be, right? You're allowed to have a point which is a critical point, but neither a max nor a min. What actually happens over here is that our function comes in, does this, and goes out this way. There is a vertical tangent, which is something we hadn't seen before in this class. Right? Now, I can give you all of the rules. I can give you, okay, so corner is what happens when the derivative on the left and the derivative on the right both have finite limits but are not equal to each other. I can tell you that for a cusp, they are both infinite but of different signs. Over here, both infinite but of the same sign. But just look at them. Right? Read the picture. The better you are at reading the diagram, the easier all of this becomes. And we're using this in order to sketch stuff. So you definitely want to be able to visualize it. So I recommend not writing it down. Give it 24 hours. And then at some point tomorrow, during whatever class it is that you have at 3 p.m., you go to this and then you figure out what these guys mean. What do they mean in terms of the limits of f prime? And if you're able to solve that, it'll get you a very long way towards being able to understand this entire chapter. So it's one of the better exercises that you guys can do. And all it does is we take the first derivative, throw it on a number line, and figure out what's what. A couple of quick, just straight lines, right? I'm not looking at what the second derivative is. I'm not looking at, is this going up like this, or is it going up like that? Increasing, decreasing, this must have been a maximum point. Right? And that's it. That's the first derivative test. In order to do anything, in order to find the critical points, you must have factored this. You must have figured out what these points are. The amount of time that it takes you to add the signs in there is almost always going to be significantly less than what you need to do for the second derivative test, which is you need to find the second derivative, and then you need to plug in those values into the second derivative. But first, you have to pray that the answer is not equal to 0. Because, or worse yet, something like this, where the second derivative just doesn't exist. Right? The second derivative test does not work on this point. It does not work on corners. It does not work on cusps. There are quite a few other types of points where it just does not work. So for the longest time, I had no idea why we even bothered teaching it. Ends up that in multivariable calculus, the first derivative test fails miserably. It just doesn't work at all. You can have functions where the first derivative test tells you that you are at a maximum, but you graph the thing and you're clearly not. There's a valley right next to you. And the first derivative test just can't figure it out. It's really, really cool stuff. The second derivative test still doesn't give you an awful lot of answers, but at least it gives you something. So be aware of the second derivative test. Right? And all you have to do for the second derivative test is you take the following. So this is second derivative test. If f prime of some point c is equal to 0, so again, this is already problematic because there are so many points where f prime does not exist. So if f prime of c is equal to 0, find f double prime of c. And then what happens? Because f prime of c is equal to 0, that means that we have a horizontal tangent. And so if f double prime is positive, we are at the bottom of that smile. So f double prime of c is greater than 0 implies that we are right here, which is a minimum. If f double prime of c is less than 0, then we are over here, which is a maximum. Okay, so you can use that, but first of all, there's the counterintuitive thing that over here f double prime is greater than 0, and therefore you are at a minimum. It makes sense. I mean, it's obviously the conclusion, but for some reason, because you're using these words that stand in some way against each other, you tend to have more difficulty remembering this. And besides, you've already done all of the work for the first derivative test, and you're guaranteed that this guy will work, while you're not guaranteed that the extra work over there will work. So why bother with it? Okay? So that's my recommendation. Obviously, you don't have to listen to me. You want to use the second derivative test all the time, you can go right ahead. I certainly see it when I mark the exams for the online calculus. But it's still extra work that you don't need to do. Okay. Let's try to graph something annoyingly difficult. Do we have time for annoyingly? Yeah. Okay. There we go. So, we'll try to graph this. We'll try to see what we can do with it. And as we do that, we will learn what the method is for putting together all of the information that you need on a graph. Okay, we're going to need to learn about increasing versus decreasing. We're going to be able to need to talk about concavity. We are not going to bother with the third derivative. Okay? Most people have a tremendous amount of difficulty visualizing what the third derivative does graphically, how it makes the function behave. And besides, once you've got second derivative, that's good enough for almost everyone's ability to look at it. So it's good enough. Right? So we're going to want to examine those things. X is equal to 2 is definitely going to be a problem. So we're going to want to look at asymptotes in general. Horizontal asymptotes, vertical asymptotes, oblique asymptotes. We're going to need limits near those. We're going to need to play around with a bunch of stuff. So let's break it into individual pieces and see what happens. One nice way of approaching it is to go level by level. So first we'll look at the physical values of y itself. All right, so first section, examine y itself. Domain is a good idea. What's the domain for this function? Yeah, x is anything other than 2. Absolutely. Anything else? It's defined. I don't have division by 0. It's good. Range, don't worry about it. Okay, you don't need to worry about the range because for a lot of these you can't even figure it out right away. And besides, you're sketching the graph. Once you've got all of the asymptotes and you just sketch the graph between them, whatever you need to know about the range is going to be there. It's going to physically show up on the graph. So you don't need to worry about range. A lot of people will tell you that you want to look for symmetry. Is the function even? Is the function odd? I'm not a fan of this. Not because it's a bad idea. As you've seen, if there's a geometrical thing to be done, odds are good that I'm leading the charge for it. But whether it's even or odd, you still have to do the same work. You still are going to have to take the derivative, set it equal to 0, second derivative, set it equal to 0. All of that stuff, all of it will still need to be done. You're not saving yourself any work. You are creating a point where you can help yourself. You're creating a piece of data which will allow you to double check your work. So if you notice that the function is even or odd, great. Absolutely write it down, keep it in mind so that when you're done with the graph, you can look at it and go, okay, is it even? Is it symmetric around the y-axis? If it is, great. I did my work probably right. If it's odd, it reflects, right? So these are the things that you're looking for. But I generally don't go out of my way to find these. But if you want, odd versus even versus neither, which is what we generally tend to get. Asymptotes. Notice I'm not bothering with x and y intercepts. They were incredibly important when you were graphing lines and when you were graphing quadratics. They're less important with something like this. Right? It is so difficult to come up with a function where the first derivative and the second derivative end up giving you nice numbers for all of their important values. That to add to that, for the function to also have nice values for f of x itself is asking for way too much. We would have like 3 graphs that we can give you. You're given 2 of them as homework and the third one is on the exam. So it's not exactly ideal. So what we do is, if you see something obvious, then write it down. So for example, if you really wanted to, you can put in x is equal to 0 and plot that one. Really, as long as you're on the right side of the axis, of the origin, we're happy. It doesn't need to be precise at all. So, asymptotes. What kind of asymptotes am I going to have? What's the easy one? Vertical, absolutely. So vertical at x is equal to 2. And the way I show this, the limit as x goes to 2 from above of that thing over there. Okay, the form that it takes is 4 plus 2 minus 2 is going to be 4 over 0 plus. So this guy goes to positive infinity. Take the time, do both sides. The limit as x goes to 2 from below of x squared plus x minus 2 over x minus 2. The form now is going to be 4 over 0 minus, which goes to negative infinity. Okay, what's the other asymptote? Slant asymptote, oblique asymptote? Absolutely. How do I figure out the oblique asymptote? Absolutely, long division. X squared plus x minus 2 divided by x minus 2. If I'm just dividing by a linear term, I can use synthetic division. But be aware that synthetic division always divides by x minus a. If this guy was, say, 2x minus 1, you've got a factor of 2 that went from one point to the other. So you've got to play with it. You've got to make sure that everything is just right. It's doable, but you need to know what you're doing. So if synthetic division is something where you're comfortable using it, but you have no idea how to translate between synthetic division and what this result is going to be, then don't do it. Just use long division. You'll be fine. Right, so x over here gives us x squared minus 2x. We subtract, get 3x minus 2. So this is plus 3, 3x minus 6. Subtract that, gives us a 4. So y is equal to x plus 3 plus 4 over x minus 2. Okay. Let's start putting this stuff together, which is going to be annoying because we're going to have to flip this board up and down a few times. But at x is equal to 2, we have a vertical asymptote. We know that on the right, the function disappears after positive infinity, on the left to negative infinity. Indicate that so that you know what you're doing. Function is coming in over here. Function is going out over there. Okay? This is an important piece of information. For one thing, even if you don't use it precisely, what you are going to get is that this comes in as a way to double check your work. What can I say about the derivative of my function when x is close to 2 on the left-hand side? Negative, absolutely. If I get some result that tells me that my function is increasing over here, then I know I made a mistake somewhere along the way. As a matter of fact, not just that, but this is going to be frowning. Right? So f double prime is going to be negative. And if I get a result that that's not the case, then again, I must have made a mistake somewhere. Either in calculating the derivative or the second derivative, or in calculating the limit. Right? Something went wrong. I can go back and I can double check. Then y is equal to x plus 3 plus 4 over x minus 2. This right here is the asymptote. So I can graph y is equal to x plus 3. Diagram very much not drawn to scale. But what happens? When x becomes a very, very large positive number, then my value for y is x plus 3, the asymptote, plus a very, very small positive number. So the value for y is the value of the asymptote plus a little bit. So my function is disappearing on this side of the asymptote. Again, not a necessary piece of information, but it's going to help make sure that all of your arithmetic is correct. Similarly, on the left-hand side, when x becomes a very large negative number, I have my asymptote plus a very, very small negative number. My function is going to be coming in a little bit below the asymptote. Okay? Useful pieces of information. Yeah?
Can you explain it again? Like
So this guy right here is the asymptote. And then this extra bit gets you from the asymptote to the value of y, to the value of the actual function. So when x is a very large number, this guy is going to be close to 0. But it's either close to 0 and positive, in which case I'm a little above my function, or it's close to 0 and negative, in which case I'm below my function. Right? Tiny little bit, but it helps to save the day a fair number of times. Yeah?
You said you're a tiny bit below the function, or
Below the asymptote. The function is below the asymptote. Yeah, I'm sorry if I misspoke. Okay? So we're good? All right. Next. So we are done with the first section. We're done with examining the values of the function itself. Now we need to add details about the first derivative and about the second derivative. So those, surprisingly, are going to be parts 2 and 3. Examine y prime. All right. So to figure out y prime, probably I'm going to want to take the derivative, but I have a choice. I now have the function written down in 2 different ways. I have the function written down the way it was originally given, or I have the function the way it was written after the long division. If you were given just those 2 choices, nothing else, no context, and you were told, find the derivative of one of these, which would you prefer? Most people are going for the second one. Right? Some people are going for the first one. Good for you. It's important to have people who are willing to take the long way around. Right? Because the first one, you've got to use the quotient rule with a quadratic at the top, a linear at the bottom. It'll take you a little while. The second one, y prime is equal to 1 plus 0 minus 4 over x minus 2 squared. Takes longer to write it than to figure it out. Great. That's exactly what we want. Right? Set this guy equal to 0. Be careful. Don't get rid of the fraction. All right? In order to be able to draw your number line properly, you want to know not just where things are equal to 0, but also where you have division by 0. So what you should do is write this as x minus 2 squared in the denominator, x minus 2 squared minus 4 is equal to 0. 2 options at this point. You can expand this and then factor the whole thing. Or, if you're feeling clever, this is a difference of squares. Right? You can factor it out as difference of squares, and you can get x times x minus 4 over x minus 2 squared is equal to 0. Feels good to be clever. So what we have for our number line are the points 0, 2, and 4. I know that x minus 2 is squared, and therefore it's not going to change the signs, but it makes it easier to have it there because it reminds you that x is equal to 2 is an important point in the function. It's certainly going to have some different things that happen to it with the second derivative. So what do we have over here? When x is a very large negative number, everything positive, negative, negative, positive. Okay. So we have a horizontal tangent at x is equal to 0 and x is equal to 4. Find those points. Okay, those are the important points. Right? The points where you can maximize and minimize things. The points where you can optimize the process that you are looking for. That's what counts. That's what we're always looking for. Therefore, you want the y values. And remember, you're looking for the y values. Don't accidentally plug it into y prime, because you're just going to get everything is at 0. For some reason, my entire function happens on the x-axis. And that's going to make things look a little bit funny. All right, so you go back to the original, either on the left or on the right, and you plug it in. When x is equal to 0, y is equal to 1. When x is equal to 4, we end up with, what would be better? 7 plus 2 is going to be 9. That's nice, consecutive squares. That's all we need in terms of y prime. Now we can take that information and we can add it to our graph. Okay, so what's going to happen is at 0, 1, which is about there, the function flattens out. Okay, notice I'm not using a point to indicate this. I'm using a very small horizontal line. This is years and years of practice have taught me this particular method. When you have just a point, and those of you who did graphing in high school probably remember this, your graph inevitably went up and then had a bit of a corner as it went back down. Or worse yet, it did this thing where it goes up like this and then just very quickly turns and then does that. Right? One way or another, it looks horrible. But when you have this line over here with a point indicating what happens, it gives you this visual guide for your hand to come in smoothly, hit its mark, and come back down. Tiny little change, you will find that the difference in how good your graph looks is really impressive. And the worse you are at sketching, the bigger the difference this makes. There are those people who can use just a dot and they can draw it so perfectly that that you use their graph in order to check MATLAB. Right? But those people aren't going to gain anything from this. The people for whom their graph looks as if a chicken ran around after being beheaded, it works a lot better. So we've got this point over here, and we've got 4,9 over here. This is enough. I'm going to go through it and find y double prime and see what that does. But right away, you can see this thing is going to increase, turn around over here, drop down. This is going to decrease, hit this apex, and go off that way. Right? Almost all of the information is right there, and you're just one derivative in. For completion's sake, examine y double prime. So, I can take the derivative of y double prime as it's seen over here, or I can take the derivative of y double prime as we have it over here. This better not be an actual option for you guys. You shouldn't have to think about it. Right? This over here, you've got a quadratic over a quadratic, and you would have to use the quotient rule for that. This over here, y double prime is equal to 0 plus 8 over x minus 2 cubed. Done. Equal to 0, negative, positive. Not a bad idea on the number lines to add this. Notice over here, because I already know that the function is discontinuous, I'm going to have a break in these. You don't have to, it doesn't make a difference. Over here, negative makes us sad, positive makes us happy. And all we need to do is take that information and relay it to the graph itself. Not a bad idea to have a line at the very bottom of your graph where you put in the information that you've just learned. So, for example, we know that the function is increasing over here, decreasing over there, decreasing down to this point, increasing after that. We know that the function is a hill over here, a valley over there. So you do that at the very bottom, maybe even put a line to indicate that it's not part of the graph itself, just in case your TA is not sure what they're doing. And now you can connect all of this. So let me just fix the oblique asymptote because it's not a straight line. And what we're going to have is this guy's going to come in, turn over here, vanish that away, and then coming in from positive infinity, decreasing, slowing down, you hit your mark over here, and you vanish off in that direction. Because my scale is awful, it's not as symmetric as it should be. But that's it. So whenever we are asked to graph a function, you examine y prime, y double prime. You put all of that information together. Using number lines is a much better idea than most of the other methods. It gives you right away where things are positive and negative, and then you can sketch that on the number line itself. And you have that rough idea of what the function is going to do. Put all of the information over here and run with it. The information about y itself, so the asymptotes, you can leave that till last. Like if you want to, you can just figure out the domain right away, and then do y prime, y double prime, and then look for asymptotes. For me, honestly, It depends on the function. There are some functions where I end up doing all of this work right away, make sure that it's correct. Other ones, it waits until the very end. Usually I remember to do it. Not always. Okay. Any questions about any of this? Yeah.
I'm just looking at part 2, the examined y prime. Is that for us to determine the horizontal tangent eventually?
Yeah, so examining y prime, you get the horizontal tangent, but you get much more than just that. So it gives us the points where y prime is equal to 0, where we have the horizontal tangent. It also gives us the points where we have a vertical tangent or a cusp or any of those variants. You get them showing up on the line itself, on the actual number line. And then between those, you also want to figure out increasing versus decreasing. So there's a huge amount of information there. That's why by the time we got to the end of it, we already had a good idea of what the graph was going to look like.
And sorry, the horizontal tangent there is only 0 and 4 because there's a discontinuity actually, is that right?
To be more precise, so the horizontal tangent is at 0 and 4 because that's where y prime is equal to 0. At 2, the problem is the division by 0. Even if the function existed, even if the function was continuous at x is equal to 2, the derivative doesn't exist. And it's the thing that breaks it, and you will end up with, in this particular case, you would end up with a vertical tangent. Okay? Yeah?
Could you please repeat how to find the horizontal tangent again?
So horizontal tangent is just y prime is equal to 0.
Okay.
Right? So the important points that we have, right over here, we've got y prime is equal to 0. Right? Because those are the ones where the shape of the graph is very, very clear. So it's important for us to be able to see them. Also, there where we have optimized points, a maximum or a minimum. So we definitely want those as well. Okay? So we're just looking for where is y prime equal to 0. So the numerator is equal to 0, not the denominator. Okay? One of the things that we will look at next class is the points where y double prime is equal to 0. This doesn't have any of them, but some of them are referred to as inflection points. We'll work out the details then. Yeah?
Oh, so I was wondering if we have the sign diagram where we are examining the y double.
So if we have the,
If we already have the sign diagram, so there's no need to examine the y double.
always look for y double prime because inevitably we're giving you marks to do it. Yeah. So even though we had gotten to this point where we were like, okay, we know what the answer is going to be, figure out y double prime anyway. At the very least, it double checks your work. Okay? Yeah. Horizontal asymptotes is limit to infinity. Limit to either plus or minus infinity if it's a constant. Yeah. Okay. Friday, we'll graph something else, maybe two somethings else, and go on from there. All right. Have a good day.